Hello, I'm Mariana, and I will be presenting the paper Kicking the Bucket, Fast Privacy-Preserving Trading Using Buckets. This is a joint work with John from the University of Bristol, Antigoni from JP Morgan, and Nigel and Younes from KU Leuven. Our work is about trading in dark pools, so I'll start by explaining what dark pools are and why they exist. In a typical lit market, investors will submit orders to an auction whenever they wish to buy or sell some quantity of stock at a particular price. And the information in their orders becomes public as soon as they are submitted. In an auction with a limit order book, for example, we will know exactly who wants to buy or sell something, as well as the quantity and the price they want to trade it for. Now, suppose that at a certain point, someone submits this large buy order. The volume to be traded by this order is quite high, so it will take a long time for this order to be completely filled. And if anyone wants to buy some of this stock in the meantime, they will have to provide a better price. And because of this, whenever a large buy order is submitted, prices will tend to go up. And the other way around, whenever a large sell order is submitted, prices will tend to go down. This effect is known as price impact, and it can actually be quite costly for large volume investors. And because of that, there is this new type of trading venue that was created called a dark pool. And in a dark pool, the information contained in the orders is kept hidden from the public until the trade happens. And then there's this dark pool operator who will be the one seeing the orders and who will process the auction according to some predefined mechanism. So this is great for avoiding the price impact because investors don't even have access to the information in the dark pool. But well, there's still a problem, which is the operator. So we cannot really be sure if the operator is behaving honestly. And well, in fact, there have been already quite a few situations where the operator was indeed found to be misusing customer order information for their own advantage. In this work, we address this problem with the operator by using multi-party computation, or MPC. With MPC, what we'll get is basically a decentralized trading system where the order information is never in the clear. There will be a set of computational parties who will process the auction, but not even these parties will actually see the order information. Of course, that for real-world deployment, it is also important to know who could play these computational parties. And one option would be having, for example, something as in the turquoise Plato and Cross. The turquoise Plato and Cross is a large dark pool owned by the London Stock Exchange Group, and it works in agreement with a group of institutions, and this includes several investment banks. And these institutions could potentially act as computational parties on a rotating basis in this MPC solution. There is already some work on using MPC for protecting dark pools. For example, the paper MPC Joins the Dark Side from 2019. And in that work, the goal was implementing different auction mechanisms using MPC, analyzing these mechanisms and the performance, and see if MPC is indeed a good solution for this use case. They implemented 3 different auction mechanisms, and out of these, the volume matching algorithm implementation had good enough performance to be able to handle real-world trading. So in this volume matching algorithm, the orders have no price information, and they are matched based only on their volume, and then the price is taken from some reference exchange. What we do here in this work is focus on building algorithms that are faster and have better privacy than before. So we propose 2 algorithms, and the first one is an improvement of the volume matching from the previous work, where we add this check of input correctness, and this will fix a problem that wasn't addressed at all before. And we also do some changes on the procedure for clearing orders. Then we introduce this new algorithm called bucket match. And well, this actually works in a similar way as the volume match, but all the orders have the same volume. And we'll see later how this works. And then we also introduce the possibility of submitting these 0 volume orders that we call dummy orders, and they will help preventing information leakage. Before talking more in depth about the new algorithms, I'll go over some important things about MPC. So with MPC, we can have a set of computational parties who calculate a function over private inputs, and only the final output is revealed. And in this work, we will use MPC based on Shamir secret sharing. So the secret inputs are encoded as the constant terms of polynomials. And the protocol has active security with the board assuming honest majority. And this means that as long as we have a majority of honest parties, the adversaries can arbitrarily deviate from the protocol, and the honest parties will just notice this misbehavior and they will abort the protocol with overwhelming probability. When using MPC, it is important to be careful with the cost of each operation. For example, additions can be performed locally, but multiplications require one round of communication. Then there are some more expensive operations, for example, comparisons, which require 7 rounds of communication. Another relevant thing is that conditional branching and data-dependent memory accesses will leak information. So we cannot just perform the same operations as we would when implementing algorithms in the clear. And we actually have to find some workaround that will avoid this information leakage. In the MPC protocol we will be using, there's both an offline phase and an online phase. And in the offline phase, we do some computations that are independent of the inputs, so we can run it while the market is still closed. And as an output, we will get these two data types, the bits and the triples. Then in the online phase, we will compute the function that we actually want to know the output of. In this case, we will process the auction. And during this computation, we will use the pre-processed data, so the bits and the triples, and this will allow us to compute the online phase a lot more efficiently. Okay, so now we move on to the auction algorithms. And the first one is the bucket match. And actually, there are two versions of the bucket match, the version with one list and the version with two lists. In the version with one list, we have that every order has the same predefined volume. We might still have dummy orders, which are orders of zero volume, but as soon as an order has positive volume, then it will be this predefined volume. Of course, that an investor might want to submit more than this volume to the auction, and in that case, they can submit multiple orders. Because the orders have all the same volume, it is possible to process them very fast. But the problem is that we might have several investors submitting multiple orders. So we will probably end up with a lot of orders to process. And so this is sort of a trade-off here. And to try to improve this, we introduced the version with two lists. And the version with two lists is similar to the version with one list. So inside the same list, we have orders with the same volume, but each list corresponds to a different volume. So there will be a list with higher volume so that investors wanting to submit a very high volume can use this list. And then there will be a list of lower volume. Then, of course, it might happen that in one list there's some leftover buy volume, while in the other list there's some leftover sell volume. And in those cases, we will need this additional cross-list matching, where we match, well, the sell orders from the first list with the buy orders from the second list, for example. Then in the volume match, we have again one single list, but now orders can have any non-negative volume. And this means that investors can submit one single order independently of the volume that they want to trade. So in general, we will have less orders to process in the volume match than we had in the bucket match. However, there's this input correctness check that we require the orders to pass. And this is required because we are working over finite fields, and so we do not want overflows to occur. And to prevent this, we will actually enforce an upper bound on the volume of the orders, but this upper bound is high enough that investors can still submit orders of very high volume. And then we also have a slightly more complex clearing phase, and I'll explain that later on with an example. Now we'll look at the order format, and we'll see which information is contained in the orders for both of the algorithms. Notice that this information is all in secret shared form, so it will all be private. Now, for both the bucket match and the volume match, there's this ID, which is the identity of the person who submitted it. And then for the bucket match, we already know the volume of every order because all of them have the same predefined volume. And because of this, we only need information about the direction of the order. So we need to know if it is a buy order or a sell order. If the order is a buy order, then the sell bit will be 0 and the buy bit will be 1, and the other way around if it is a sell order. We can also have dummy orders, and in this case, both the buy bit and the sell bit will be 0. For the volume match, we again have a buy bit and a sell bit, which tells us the direction of the order, but now we also have some information about the volume. Now, as I mentioned before, we need this volume to be below a certain bound, and in order to enforce this, what we'll do is that we'll require this volume to be written as a sequence of bits. So in fact, this information about the volume will not consist of a single value, but actually a sequence of values, and each of them will be a bit. So notice that both order types, they have basically a sequence of bits, except for the ID part. But because these values are in secret shared form, we don't actually see if they are really bits. So we need to perform some check to see if all of these values are bits. To do so, what we do is check that this equality down here holds for every value that is supposed to be a bit. And notice that this will only hold if x is either 1 or 0. Then there's another check that we need to perform because although we allow orders that are neither buy nor sell, we do not allow orders that are both buy and sell. So each order will also have to pass this check, so this equality will have to hold for every order. So for every order we receive, we will check if these equalities hold, and if any of them doesn't hold, then the order is discarded. So in fact, we have a input correctness check for both the bucket match and the volume match, but since the volume match has this volume information that is written as a sequence of bits, the check will be a bit longer and more expensive. Finally, for the volume match orders that pass the check, we will take the sequence of bits representing the volume, we will use it to calculate the actual volume, and then we will multiply this volume by both the buy bit and the sell bit, and we will rewrite the orders in this form here. Now, just to note that in the previous work from 2019, the direction of the order was actually public, so only the order volume was hidden, and so this is already an improvement over the previous work in terms of privacy. Now we'll see how the orders are matched, and to explain it, I'll use this example here. So the first step is the input correctness check, which I'm assuming that all of these orders in this list have already passed. So all of these orders are in the correct format. And then to match the orders, we'll first have a clearing phase one. And in this clearing phase one, we'll start by aggregating all the buy volume and all the sell volume. So in the bucket match, for example, we have a total buy volume of 1 unit and a total sell volume of 3 units. And then we compare these two total volumes and we reveal which one is larger. So in the bucket match case, we have more total sell volume, and in the volume match case, we have more total buy volume. And now you observe that the orders in the direction with least total volume will actually be all matched. So we can just open all the information in that direction. So in the bucket match, we are going to open all the buy bits. And in the case for the volume match, we are going to open all the sell volume, since we know this will all be matched. And for the orders that actually have some volume in this direction we just opened, we also open the ID, since they will be trading this volume. Now, in the previous work, instead of opening the orders in the direction with the least total volume all at once, we would actually be opening each order one by one and performing a comparison for each open order. So this is definitely an improvement in complexity of the clearing phases. Now we look at the orders that had zero volume in the direction that we just opened. And notice that we don't really know if they are an order in the other direction or if they are a dummy order. So here we start seeing the advantages of having dummy orders. And in particular, in the bucket match, if we didn't have these two dummy orders we have here, we would know exactly how much volume is left. So because of the dummy orders, we cannot really tell just by looking at the number of orders how much volume there is in the bucket match auction. Then we move on to clearing phase 2, where we will open the orders in the other direction. And here the bucket match and the volume match are a bit different. So we'll start with the bucket match. And in the bucket match, because every order has the same volume, we can just open the cell bits one by one until the buy volume is completely matched. So first we'll open the cell bit of the second order, and it turns out that this order is a dummy. And then we open the cell bit of the third order here. And because this order has cell volume, the buy volume is already completely matched, and we can stop opening orders. Then for the volume match, we can try to do something similar where we open orders one by one. However, because in the volume match, the orders can have different volumes, if we do that, we will run into a problem. So let's say we open the orders one by one. So the first order with buy volume is this one with volume 3. And then in the sell side, we have a total volume of 7 to trade. So after opening this order with volume 3, we will be left with 4 volume units left to trade. Then the next order with some buy volume is this order with buy volume 5. And note that if we open this volume, then we know that there will be 1 volume unit left to trade here. And we don't want this to happen. So we don't want to know about some volume that still hasn't been matched. So we have to figure out a way to open the order such that this doesn't happen. And the way we solve this is by performing a binary search to figure out which is the first buy order that surpasses the total sell volume. And in this case, it's precisely this order of volume 5. And so we don't open this order, we open all the previous orders. And when we reach this order, we just check how much volume we are still missing to completely fill the sell side. And we just subtract this volume from this order. So here we had still 4 volume units in the sell side. We subtract 4 from the volume of that order, and we are left with 1 volume unit. So now we know that this person with ID 1 traded 4 volume units, but we have no idea if they still have some volume left to trade or not. And if they do, we have no idea how much this volume can be. So we have seen how the bucket match works, but actually you only saw the case with one list. And well, the two list case is similar. In the beginning, we just perform clearing phase 1 and clearing phase 2 in each of the lists. But then it gets a bit different if we have cross-list trading. So here in this list we have here, there's some leftover sell volume. And if in the other list there would be some leftover buy volume, then we could do some cross-list trading. And the problem is that when we do cross-list trading, then we are matching orders of different volumes, which is a similar situation to the volume match. So this case where we have some partially matched orders can also happen. So we might have this leaked volume that won't be matched. And we could try to do something similar as we did in the volume match, where we just subtract the volume from the order without actually opening it. But actually, when we have the bucket match with two lists, we know exactly what's the volume of every order. So even if we do this, we don't open the order, we just subtract the volume we need to trade, we will know exactly what the volume of that order was. So this leakage is inevitable. And this means that if we use the bucket match with two lists and there is a cross list matching, which might not be the case, there might not be a cross list matching at all. But if there is, then there's a possibility that we will have some leaked untraded volume. Here we have a table comparing the three algorithms. In terms of submitted orders, the volume match is the one with least orders, since investors can just submit a single order independently of the volume they want to trade. While in the bucket match, they might have to divide their volume into several orders. In terms of computation, the bucket match with one list is the one with least computation. Then for the volume match, we have to perform the correctness check for the sequence of bits representing the volume. And for the bucket match with two lists, we might have a cross-list matching. In terms of leakage, as we saw before, the bucket match with two lists might have a leakage coming from the cross-list matching. Then there is the missing volume that I haven't mentioned before, and this might happen because when submitting orders to the bucket match, the investors might have to divide their order into several orders. And if the volume they want to trade is not a multiple of the order volume, then there might be some volume that they would have submitted otherwise, and that won't be submitted anymore. In our experiments, we ran MPC using three computational parties, which are three machines in a local network. And we did experiments varying the number of investors and also the number of dummy orders submitted for each true order or each order with actual volume. And then we suppose that investors would submit a volume that is taken from this distribution here that was selected by an investment bank. And in the case of the volume match, each investor will simply submit a single order with the volume taken from this distribution. And for the bucket match, they will take the volume from the distribution and they will divide it into the necessary orders for the bucket match. There's also an imbalance. So there's more investors that are buyers than investors that are sellers. And this was also selected by an investment bank. Here are the runtimes for 1,000 investors, and this corresponds to the online phase of the MPC and includes both the computation for the input phase and both clearing phases. And the parameter D is the number of dummy orders submitted for each true order. So we can see here that the bucket match with two lists seems to be the algorithm that's faster, but we have to remember that in this algorithm, there's a risk of having some leakage. So this is not a good algorithm to choose if we want to be sure that we don't have leakage. And actually in our experiments, because of the distribution we were using and also because of the buy and sell imbalance, we actually never had cross-list matching. So in our case, we never actually had leakage. But yes, so depending on the specific order distribution, we might get some leakage, and this is a possibility with the bucket match with two lists. Then for the volume match and for the bucket match with one list, they seem to have very similar runtimes for each value of t, but we should notice that for the volume match, the dummies are not so relevant because even if we know the number of orders that are left to trade, they might have any volume and we have no way of predicting it. While for the bucket match with one list, the dummies are essential for hiding the volume that was left untraded. So in the bucket match with one list, we will typically have a high number of dummies, while in the volume match, we will have zero or almost zero dummies. So the volume match will actually be generally faster. And even in the bucket match with two lists, because we'll also need the dummies, the volume match will actually have a comparable runtime to the bucket match with two lists, or it might be even better. Then we also have some runtimes for 10,000 investors. So I just wanted to notice that here, if we consider the volume match algorithm, since we will usually have very few dummies, we will be matching the orders from 10,000 investors in around 10 seconds. To conclude, we show that MPC can be used to emulate the operator of a dark pool with runtimes that meet real-world requirements. And we improved the previous work by simplifying the clearing phase, by introducing the input correctness check that is necessary to avoid overflows, and also by introducing dummy orders to increase the privacy. Thank you.